In this video, we're going to discuss significance testing and how it relates to the second half of this course. When I think of significance testing, I think of trying to test a claim, trying to test something that has always been known as the best way of doing things or something that we just have come to accept. Like, for example, I always go back to think back to the early 20th century and even later into some of our parents' lifetimes where smoking was not deemed to be a health risk. And now what we've done is obviously prove that it can have serious health risks and associated to cancer. So the null hypothesis in this case would be that the smoking does not affect one's health. Whereas the alternate hypothesis would be if we think of null hypothesis as like your status quo, as the old way of thinking, the traditionalist, the conservative type of thinking, the alternate hypothesis rather would be something more innovative, more experimental, a little more radical thinking, and something that takes a little bit of research to do. So in this case, you would do the numbers and try and figure out the patients who have been smoking for years and see if there is a correlation between that and cancer. And your alternate hypothesis in this case would be that yes, okay, smoking does influence one's health and is detrimental and increases their risk of cancer, so on and so forth. So that's a general way of describing the two terms that are really the backbone behind significance testing. And just before we move any farther, I'm just going to write both of those down. So we have a frame of reference here. So you have your null hypothesis, and that's often symbolized by a capital H with this sub, we call that sub naught, or it's like a sub with a little O. And that's again, that's your status quo. It's usually a statement of no difference. And then you test it with what's called your alternate hypothesis. Okay, and we're going to look at another example here in a minute that shows these two and how they combat each other. It's kind of like a rival. Okay, your alternate is on one side of the argument, your alternate hypothesis is on the other side of the debate. Okay, so you'll see to my right here, I have two different pictures. I have a cup of Starbucks coffee and then a bottle that contains Nescafe instant coffee. Okay, and in this example, what we're going to say, I'm going to try and prove that in this case, let's say I'm a marketing representative for Nescafe. Okay, so this is a product I'm trying to sell. Okay, and I'm trying to say that this product over here, this Nescafe Classico, tastes just as good as Starbucks coffee, which hopefully already, if we know anything about coffee, or at least have an idea of what's going on there, the Starbucks is probably obviously going to be a better option than the Classico instant coffee. But my view is biased as a marketing rep for this company. I'm going to try and show that again, what we've created here is the same as Starbucks. So we do a blind taste test. All right, that's the first thing. We're going to do a blind taste test where we have a sample size of 100 people, and they're going to be given both the Starbucks and they're going to be given both the instant coffee. And we're going to try to determine if it's a 50-50 split. So if the claim I'm making is that this coffee over here is as good as the coffee in Starbucks, I would expect that out of these 100, 50 people, right, would prefer the instant coffee, and 50 people would prefer the Starbucks. Okay, if it was any other breakdown, let's just say what I might expect as the cynic is maybe 90 people would prefer the Starbucks. Even with a blind taste test, they tell a difference, and then 10 would prefer this. Okay, obviously this 90 outweighs the 10, so it would lead me to believe that more people are promoting Starbucks. Okay, but again, I'm going to say my null hypothesis here is that 50 out of 100 people, okay, we're going to say P is equal to 50%. In other words, the proportion of people who prefer Starbucks over Nescafe is 50%. Okay, that would lead me to believe that there's no difference between the two. It's just totally random. So that right there is going to be my null hypothesis. My null hypothesis is that P is equal to zero point 0.5 or 50%. Okay, and again, we're going to call that P is the proportion of people who prefer Starbucks. Okay, and another way to think about it is there's no difference between the two. Okay, now as the cynic, let's think back to this. Like, let's again, as crazy as the claim as it once was, smoking is not bad for your health. I think again, if you're in tune to coffee just a little bit, it'd be very naive to think, okay, the Starbucks is going to taste the same as this Walmart Nescafe brand instant coffee, right? So as the cynic, as the someone who's being a little more radical, someone to try and prove a point, okay, I'm going to say that I think the proportion here, the proportion of people who would prefer Starbucks over Nescafe is more than 50%. Okay, I don't have to put a value on it. I don't have to put, I do want to put a direction on it. I just want to say it's greater than. Okay, so again, to just put these null and alternate hypothesis in terms of words, we're going to say that the proportion, basically the same thing we wrote down there to the bottom, we'll say, and we'll just abbreviate here. So the proportion of people who prefer Starbucks is 50%. Okay, again, as the cynic, my alternate hypothesis is the proportion of people who prefer Starbucks is more than 50%. Okay. Now, again, I don't know what that number is going to be or what I'm going to use to test that. So down here, I'm going to section this off. We're going to do our test. So if I'm the one who's saying that, you know what, I don't think that's going to be true. I think the percentage is going to be higher. Okay, well, I actually have to create my own blind taste test. And let's say when I conduct that in my test, so we'll say we test 100 people, and in that test, 62 preferred the Starbucks. Okay, in other words, my sample proportion, P hat, is equal to 62 over 100 or 62%. So already, hopefully, you're formulating in your mind that, okay, well, I got 62%. That's a value obviously greater than 50%. So I'm off to a good start. My argument here is off to a good start. I have to show what's called statistical significance, though, in order for it to be a valid point. Okay, so how do we do that? We calculate a z-score. Okay, so if you remember, the formula we've used before is z is equal to the observation minus the mean all over the standard deviation. Now, for significance testing, I like to use a similar format, and this is just my way of doing it. I like to say z is equal to the new minus the old all over the standard deviation. Now, some textbooks will use some statistical jargon like mu, x bar, standard deviation, and those are all well and good, but you're always going to have, no matter if you're dealing with proportions or probability or means, you're always going to have a value that's new. You're always going to have a value that's old. So with regard to this example, the new value would be 62%, right? That's what I just did. I just took an experiment where I found 62% were in favor of Starbucks. So that 62 would go in the first part of our equation. The old value, or the old mean, would be the 50%. Okay, that's what we're assuming is to be true. And then the standard deviation, we can base that off our sample. It's going to look like this. So z is equal to, we're going to go 0.62 minus 0.50, and then divide it by the standard deviation, which is going to be the square root of, remember, for any proportion, for any probability, we can use this equation, 0.62 times 0.38 divided by 100. All right, so this is going to be point in the top. We're going to have 0.12. And if you give me a moment here, we'll calculate that standard deviation. So 0.62 times 0.38 divided by 100, and then take the square root of it. I get 0.0485. I'm going to round that to 0.05 for right now, just to make things a little bit easier. So 12 or 0.12 divided by 0.5, I get a z-score of 2.40. Okay, 2.40. Now I'm going to stop there for just 1 second. Okay, we're going to come back to that z-score in a minute. But I want to visually look at what we're trying to prove here. Okay, and basically what this 2.4 is telling us, let me just highlight this z-score. Remember, z-score is an interpretation of how many standard deviations to the top or to the bottom a certain value is. So what this is telling me is if we were assuming that this claim was to be true, if there was truly no difference between the Starbucks and between the instant coffee, in one sample, to get one sample, that's 62%. It's almost 2.5 standard deviations off from what we would expect. Okay, think about that. In one point in time, if I were to draw let's call this a density curve of what's going on here. Okay, here's your normal curve. And this is going to be a distribution of all the samples that I would get. I would expect most of my samples to fall right here at 50%, right? But mine was 2.4, almost 2.5 standard deviations greater than what I would expect, okay? Compare these two regions. Compare, like, this is what I would expect, right? Somewhere right in here. If it were true, maybe I had a percentage of 51 or 53, or maybe even like 45, you know? I could expect something in that area. But in the one trial, in the one sample, the one test that I did, where do I wind up? I'm all the way over here, right? 62%. Okay, which is a little off, right? It's like your friend who says that they can shoot 80% from the free throw line, and then you go out and you shoot 10 free throws with them, and they get 1 out of 10, right? Even though it's just one time that you're doing it, you're probably starting to doubt that claim of, hey, I can shoot 80% from the line. You go out golfing with one of your buddies, they say they can shoot 85, or they typically shoot in the 80s. The one time you go out golfing with them, they shoot a 135, right? You're starting to doubt that the first thing they said is actually true. So it's kind of the same situation here. The 62% is way off. So let's go back to the z-score and figure out exactly how far off it is. So using the z-score of 2.4, we're going to calculate a p-value. We need to figure out what a p-value is. All right, and a p-value is just the proportion that you gather from that z-score in the chart. So let's look up a z-score of 2.4 in our chart. Let's see what we get. So 2.40 gives me I just highlighted here, 0.9918. I'm going to round that to 0.99. So what this tells me is that all this area to the left, 0.99 or 99%, okay? And this area in the green right here, that's our p-value, okay? That's 1%, okay? Or a p-value of 0.01, okay? Or again, 1%. Okay, what this means for me, and you're probably asking, well, why do we use the 1% and not the 99%? P-value, I'm going to say, is always a measure of tail end area. Okay, for example, look at the tail. If I go to the alternate hypothesis here, I'm trying to prove the proportion is greater than. 50%, right? So greater than, I want the greater than area, right? The tail end of the area. The other tail, the 99%, is less than, so I don't want to use that. Okay, if I was trying to show proportion where it was less than, then I'd use this tail over to the left, somewhere over here in this neighborhood. Okay. Now, more importantly, is interpreting this 1%. Okay, basically what this means is if I see a p-value that's very low, I reject the null hypothesis. Okay, so I reject the null. I can't say for certain that the proportion is greater than 0.50, but I would say there is significant evidence against p being equal to 0.50. Okay, or significant evidence that there is no difference between the instant coffee and the Starbucks coffee. Okay, there is something going on there. More people would prefer the Starbucks coffee. Now, interpreting this 1%, real quick, that would be if the null hypothesis, assuming it were true, assuming that there was no difference, the likelihood that I gather a sample that's this far off from my mean would happen 1 out of 100 times. Okay? And that's the real reasoning behind this. That's the reason why, oftentimes we program our students to think the lower the p-value, we reject the null hypothesis. The lower the p-value, we reject the null hypothesis. But they're never really truly taught, like, well, why is that the case? Why am I following that equation? And the reason is it's an expression of how likely this sample would occur given the null was true. So if given the null was true, if given that this is equal to 50%, to get something this far off only happening 1% of the time in theory, yet on the only time I conducted an experiment, it happened, it leads me to believe that there's something systematically wrong. There's something that's wrong with this. So that's why I reject the null hypothesis.